This is one of my 15 top 5 chapters in the subject of physics. Impulse and momentum is very interesting subject. We got a lot of great demos. In fact, one of the demos that we shot for this chapter has become somewhat of a phenomenon around the USU committee or USU community. So hope you enjoy this. We're going to talk about the Impulse-Momentum Theorem. We're going to define impulse, we're going to define momentum, and then derive the Impulse-Momentum Theorem, which will be a stepping stone, just like the work-energy theorem was a stepping stone to the conservation of energy. The Impulse-Momentum Theorem is a stepping stone to the conservation of momentum, which is one of the most powerful, well, together with conservation of energy, is among the most powerful physics concepts out there, period. It's very, very powerful. So let's first define impulse. The impulse is the product of the average force. So what we're going to be thinking about now is the collision between a baseball and a baseball bat. So that'll be our kind of example. And we're going to ask about the force that the bat exerts on the ball during the collision. So we're not talking about as the ball is approaching the bat or after it's left the bat. We're talking about the time during which the ball is in contact with the bat. That's the collision. And you say, well, how long of a time is that? Well, it's a very tiny fraction of a second, as you might imagine. But during that time, the force between the ball and the bat is very, very strong, and we'll do a calculation to show how strong that force is. But what we're interested in defining impulse is the average force during that time. So you can imagine that when the ball first makes contact with the bat, or the bat with the ball, either one, the force isn't very strong. But then once the ball is smashed around the bat, we'll show a picture of how a ball actually smashes around the bat and it's fully in contact with the bat, then that force is going to be huge. And then the ball is going to start coming off the bat, the force will lessen. So the force might have an ugly looking shape. The force as a function of time, where this is the time at which the ball contacts the bat, and then t naught, and then t final will be the time that the ball leaves contact with the bat. So the force starts out small, just as it's beginning to make contact, gets really huge and maybe follows some ugly shape, and then goes down to 0. So the average force, this F with the bar over the top, is called the average force. If we find out the total area under this, and then we create a rectangle between T naught and TF that has that same area under it, then the height of that rectangle is the average force. And that's what we're interested in. It's a measure of, just a measure, overall measure of that force. And in many cases, what we'll be interested in studying impulse momentum is, what is that force? In fact, we'll actually calculate it for a ball, a bat hitting a ball. So the impulse itself is denoted by the letter J, capital J, and it is a vector quantity. So there's an actual direction to it. And the direction of it is the direction of the average force. So there's the average force measured in newtons, and we calculate it using this way. We won't go through the procedure for actually trying to figure out what the force is from some very complicated force versus time. We'll always just deal with this average here. So that's the average force. The time interval, that's equal to the final time minus the initial time in the usual way. And then if you multiply that average force by that elapsed time, the time in which the collision occurs, then J is the impulse. It's just the product of the average force times time. It's a force times a time. What are the units of it? Well, force is measured in newtons, time is measured in seconds, and so the average force I'm sorry, the impulse is measured in Newton seconds. So when I was little and when my kids were little, we play with these model rockets. They're maybe that high. These little engines that go inside of them are maybe that tall. Some of you may have played with them as kids. A typical model rocket engine delivers an impulse of maybe 10 to 30 Newton seconds. And you can actually look up, there's a D, it looks like these are the C63 engines, and each of them are rated by their impulse. The space shuttle rocket booster, rocket motor, has an impulse of 1.3 billion Newton seconds. So that's just to give you a little bit of a scale, the difference between a model rocket and a real one. So let's define linear momentum next. The linear momentum is the product of the mass and the velocity of an object. And you'll see why linear momentum is important, especially when we get to conservation of momentum. You might say, well, why would you want to take the product of the mass and the velocity? And the answer is that in many cases it is a conserved quantity, meaning that it doesn't change with time. So the momentum is denoted by a lowercase letter p. It's a vector, and it's proportional to the velocity. So the momentum of an object is the product of the object's mass and its velocity. So the mass of the object measured in kilograms, the velocity measured in meters per second. The velocity is a vector, so the momentum itself is a vector that's in the same direction as the velocity. That's momentum. And in fact, momentum is in many ways it's a more fundamental quantity than the velocity itself, even though you might not have had as much experience with it as you have with the velocity. So the Impulse-Momentum Theorem is starting off with a friend of ours called Newton's second law. And what we're doing is taking Newton's second law, which is the net force equals the mass times the acceleration. Net force on an object is the object's mass times its acceleration. And then we're asking about the average net force. So we put a bar over the top of that to denote average. So what we can do now is remember the definition for the average acceleration. So the mass just comes along for the ride. The average acceleration is the final velocity. It's delta v, the final velocity minus the initial velocity. This is what we called delta v, divided by delta t. That's acceleration, average acceleration. But if we multiply through by the mass, lo and behold, what happens? So we just distribute this mass, multiply it by this velocity, minus that mass times this velocity, we get this. So what would you say this is? Mass times the final velocity. You might say, well, that looks like the final momentum, doesn't it? Because the momentum is the mass times the velocity. And sure enough, that's what it is. This m times vf is the final momentum. M times v naught is the initial momentum. And what we have now shown, if we multiply both sides of this equation by delta t, so I'm going to multiply this side of the equation by delta t, this side of the equation by delta t. The delta t's cancel on the right-hand side, and on the right-hand side, all we get is this numerator, which is mvf minus mv naught, final minus initial momentum. And then over here, lo and behold, what do we get? It's the impulse. Remember, the impulse is the average force times the time. Now, this is a little bit different. This is the net impulse. When we defined impulse, we defined it for some particular force. For example, the force of the bat on the ball. How does that particular force of the bat on the ball, the average force of the bat on the ball, how does that compare with the net force on this ball? Well, let's look at the forces on this ball. This force is the force of the bat on the ball. What other forces might there be on this ball? And we can consider this force to be like a normal force, right, because it's normal to the surface. Well, it's got gravity acting down on it. It might have some air drag if it's moving through the air. I'm trying to think what other forces there might be, but those are the main forces. But let's compare the magnitude of this force of impact, force of collision of the bat with the ball, to gravity. Which do you think would be the stronger of the two forces? Well, we'll do a calculation to show you what that force actually is. Turns out it's way, way bigger than gravity. And so essentially during the collision, you can ignore every other force besides the force of collision because they just don't cut any ice whatsoever. There's just no, they're completely negligible during that collision. And if you don't believe me that you can ignore gravity, then take a baseball and balance it on your finger. That'll give you a measure of the force of gravity down on the baseball. And then take your finger and put it right at the point of impact where the ball comes in and the bat hits it. And compare how much damage you'll do to your finger by holding up the ball against gravity versus feeling the force of collision. And I think you'll agree at that point that that force of collision is going to be greater than any of the other forces. Okay, so essentially what we're saying here is that this net average force that appears here, you really only need to worry about the force of collision and you can ignore all the other ones. That's the Impulse-Momentum Theorem. It says impulse on this side equals the change in the momentum. We can write this another way, delta P. This is the final momentum, Pf, and this is the initial momentum, P naught, where Pf is mvf, and P naught is mv naught, and this delta P is just Pf, final, minus initial. So there's the change in the momentum, and here's the impulse for the Impulse-Momentum Theorem. Let me show a video. And this one's just a YouTube video. Okay, the bat, slow motion, the bat hitting the ball. Watch the bat. Okay, that is really quite a striking video of the extent of the force that a bat exerts on a ball. You can also see that in this picture here. You can see that the ball is deformed. It's mushed around that bat at the point of greatest contact. The force requiring, or the force that causes a ball to deform that much is a pretty amazing force. Let's actually calculate it. The mass of a baseball is 0.14 kilograms. It has initial speed 38 meters per second. That's going to be somewhere around 90 miles an hour, I think is what I worked it at, 80, 90 miles an hour. The typical pro fastballer, maybe, I'm not sure, but in that vicinity. Contacts a bat for 0.0016 seconds. So that's the time, the elapsed time, the time interval of the collision, T final minus T naught. Very short time of collision, like we talked about. and rebounds with a speed of 58 meters per second. So the pitch is coming in, the batter connects with the ball, and the ball is going to head to the stands. Find the impulse and the average force exerted by the bat on the ball. All right, just before the collision, here's the bat. Here's the ball moving at 38 meters per second. Let's just assume, just for the sake of argument, that the bat isn't moving at all, although it is moving a little bit. The amount that it's moving is quite small compared to the speed of the ball. So the bat and the ball, so this is just before the collision, and this is just after the collision. And this is what we'll be doing for almost all problems in this chapter, is we'll be looking, what do things look like just before they collide, and what do they look like just after they collide? And then asking about what happened during that collision to cause a change in the momentum. All right, so this is the momentum of the baseball that we're considering here. Actually, I lied when I talked about the bat not moving. It actually does move, and if it didn't move, we wouldn't have a bigger velocity here than we do here. So we actually are taking into account that the bat is moving, and I'll show you how. But right now we're going to focus just on the ball. That's the impulse of the ball. And this is the change in momentum of the ball. Okay? The ball has a mass of 0.14 kilograms. Its final velocity is 58 meters per second, and that's to the right. So this is final. That's to the right. If we take x to the right, then the component of this velocity in the x direction is going to be positive. That says that Vx final is positive 58 meters per second. Okay? That's why that's what goes here. The final x, I guess, is the way we wrote it here. Right, the f before the x. All right. Then we have the mass, which is again 0.14. It hasn't changed, and the initial velocity in the x direction. Well, here's the initial situation just before the collision. The ball is moving to the left. My x-axis is to the right. The x component of velocity is going to be negative. And that number goes right in here. All right, well, kind of a cool thing happens here. This minus sign cancels this minus sign, and we end up adding these two terms together to get a net amount of impulse. We ended up with some impulse with units of kilogram meters per second. But we talked about the units of impulse being Newton seconds. Let's double check to make sure those units are correct. What's a Newton second? Well, a Newton is the unit of force. That's the unit of a mass, kilograms, times the unit of acceleration. Force is mass times acceleration. There's your mass, there's your acceleration, and then to make the Newton, and then you have seconds here. But this seconds in the numerator cancels one of these seconds in the denominator. So 1 Newton second is a kilogram meter per second, and that's exactly the unit that we have right here. So we're happy with that unit. The impulse is about 13.4 Newton seconds. So this amount of impulse is actually comparable to the impulse of one of those model rocket engines. The difference here is that for this particular impulse of the bat hitting the baseball, it's happening over a very short time. And so that average force is huge, whereas a model rocket engine might be firing for a second or so, or 2 seconds. So that's the difference. So that's supposed to equal the average force times the time. The impulse is the average force times the time. The Impulse-Momentum Theorem says that the impulse is equal to the change in momentum. And this is just the definition of impulse. Well, we know delta t, and we know jx, we just calculated, it's 13.4, so we can solve this equation for the average force in the x direction. And to do that, all we have to do is divide both sides by delta t, and that gives us average force of the impulse divided by delta t. The impulse we already calculated, it's right here, and delta t is 0.0016. So that's average force of 8,400 newtons, and if you convert that to British engineering units, you get about 1,900 pounds. That's a pretty good size force. A lot more force than what you would see. Certainly, that exceeds the force of gravity on the baseball by a whole bunch. 8,400 newtons. The incomparable Roger Federer with his amazing single-armed backhand. Again, a collision between two objects. In this case, a tennis ball and a tennis racket. The collision lasting a very short amount of time. You would, if you wanted to analyze and find out the average force of the racket on the ball, or the ball on the racket actually, right? Because due to Newton's third law, as we will use in deriving the conservation of momentum, the force of the ball on the racket is equal and opposite to the force of the racket on the ball. All right, let's do another example which relates to one of the most famous video demonstrations that's at least gaining some traction here at Utah State University. A ping pong ball of mass 0.0027 kilograms. They're pretty light, a lot lighter than that baseball was. Initial speed 400 meters per second. That works out to be about 888 miles per hour, which is exactly the speed that we project an actual ping pong ball at a ping pong paddle in the demonstration that we're about to use. 400 meters per second works out to 888 miles per hour. This is not the Back to the Future where the professor has to get that DeLorean up to 88 miles per hour. This is 888 miles per hour, okay? Just making clear here. Contacts a paddle for 0.0001 seconds. This is an estimate of the amount of time that it takes for the ball to be in contact with the paddle. And the way that I came up with that is that we're going 888 miles an hour. The diameter of the ball is known. You can measure the diameter of the ping pong ball. I just figured out the amount of time it would take that ping pong ball to travel a distance that's equal to its diameter, which is basically what's going to happen when it'll smash against that ping pong paddle. All right, find the impulse and the average force exerted by the paddle on the ball. This is a very similar calculation to what we had before. We have x-axis to the right I've chosen. In this case, we've got the ball initially traveling to the right. And so the final, what we're assuming here in this calculation is that the ball gets obliterated and it doesn't bounce off at all. It just smashes into bits, which is actually what happens. So that the final velocity of the ball is 0. In fact, it's a complete, what we're considering it to be is a completely inelastic collision, and we'll say more about that. Minus the mass times the initial velocity, that's 400 meters per second, and multiply the numbers together, and you get a fair to middle, and that's a fair amount of impulse right there. It's not as much as the rocket or the baseball, but the ping pong ball is a lot smaller. That's supposed to equal the by the impulse-momentum theorem, that equals by the definition of impulse, that equals the average force times the delta time. Again, we divide by delta t, plug in the j that we calculated, the time, and we end up with a force of about minus 11,000 newtons. Why is that more than what we saw with the baseball? The answer is the collision time is smaller. So 2,500 pounds. let's see, what do we end up with the base? 8,400 compared with 11,000. Comparable, actually. All right, so let's do the demonstration. In physics, we're never satisfied with what we can do. We're always doing better. This is an apparatus designed and built by James Coburn, our lecture demonstrator. This is a tube inside of which we've got a ping pong ball. I'm going to evacuate this tube, take most of the air out of it. Then right about here, there's a piece of mylar, strengthened aluminized mylar with some tape on it to allow a higher pressure. I'm going to pressurize this tube, this white one, to about 100 psi. This will be at around 14 psi, pounds per square inch. This would be a vacuum, and this will be 100 psi of pressure. When it reaches the point that it breaks this mylar seal here, the air will rush from here into here, push the ping pong ball through, and then on this end I've got a ping pong paddle. That's good because you want to have a ping pong ball hit by a ping pong paddle. On the end of this tube, there's a black plastic ring and then a piece of aluminized mylar that just covers that opening, and that enables us to maintain the vacuum in here. But as soon as the ping pong ball hits that, or perhaps even the air rushing forward will break it first, then the ping pong ball will hit the paddle. And the objective here is to see what happens to the paddle. So my procedure will be first to evacuate this tube, then seal it off, and then pressurize this tube. Okay, so now we've got this guy evacuated, and I'm going to pressurize him. It won't take long, maybe half a second or so, and then you'll be listening for a loud sound and for this ball to travel. We've measured that speed of the ball with this pressure setup, measured the speed of the ball to be about 888 miles per hour, compared with the speed of sound is about 750 miles per hour. So this ball will exceed the speed of sound as it exits the end of this tube. I'll count down. 5, 4, 3, 2, 1. So this is the result. I think through the side camera you might have been able to see the result, and there's for the front camera. So the bottom line on this demonstration is if you can perfect your ping pong skills to the point where you can hit a ball at 888 miles per hour, and you can blast through your opponent's paddle. Probably blast through your own paddle too. This is a demonstration of a completely inelastic collision. Here, I believe that the product is called the egg splat. It has this kind of sticky membrane, and inside of it there's a viscous, kind of a thick fluid, kind of something that's supposed to look like an egg yolk in there too. It's really disgusting. But when you throw it at a surface, that's what happens. Normally a ball, you'd throw it at a surface, it would bounce back up at least a little bit. But this doesn't bounce up at all. It's a completely inelastic collision.